Have you ever really thought about what makes a soccer ball fly? Or how a planet stays in its orbit? Or even just what's keeping you from floating right out of your chair? The answer to all of that, and I mean all of it, is forces. They're this invisible push and pull that's running the show for every single movement in the universe.
So here's a fun one. Picture a speeding car, an astronaut just kind of drifting in space, and you, sitting perfectly still. I mean, they seem totally different, don't they? But guess what? They're all connected by one single thing: forces. In every single one of those situations, forces are right there, working behind the scenes, orchestrating this hidden dance of pushes and pulls.
And at its very core, that's all a force is. It's just a push or a pull. But, and this is a big but, don't let that simple definition fool you. This one idea is the bedrock, the foundation for explaining pretty much everything that happens in our physical world, from the tiniest atom all the way up to the biggest galaxy. So what can these pushes and pulls actually do? Well, it boils down to three main things. A force can change an object's speed, think hitting the gas or slamming on the brakes. It can change an object's direction, like when a bat smacks a baseball. And it can even change an object's shape, like when you squeeze a lump of clay. Speed, direction, shape. If any of those change, you can bet a force is responsible. Okay, so we can basically sort forces into two main categories. First up, you've got contact forces, which are pretty much what they sound like. Stuff like friction or the tension in a rope. They need objects to be physically touching. Then you have the really mysterious ones, non-contact forces. Things like gravity and magnetism that can reach out and act across huge distances without ever touching. Kind of spooky, right? Now, here's where it gets interesting. In the real world, you'll pretty much never find an object that's only dealing with one force. Just think about a book sitting on a table. Gravity is pulling it down nonstop, but at the same time, the table is pushing back up with an equal force, keeping it right where it is. It's this constant invisible tug of war. And that brings up a really big question. If we can't see these forces, and there are a bunch of them acting all at once, how in the world do scientists and engineers figure it all out? How do they actually see and calculate the winner of this invisible battle? Well, they use this brilliantly simple little tool called a free body diagram. It is an absolute cornerstone of physics. The whole idea is to just mentally lift an object out of its surroundings and then draw every single force that's acting on it. It's how we make the invisible visible. And you know what? It's way easier to do than it sounds. First, you just represent your object, a car, a planet, whatever, as a simple dot or a box. Then, for every single force acting on it, you draw an arrow pointing away from that dot. You can even make the arrows for stronger forces a little longer. And finally, you just label each arrow. That's it. You've just created a map of the invisible world of forces. Okay, now for the most important part. If all the forces on your diagram are balanced, which just means the arrows pointing in opposite directions are equal in length, then nothing changes. The object just stays put or keeps moving at a steady speed. But if one force is stronger than the others, if they're unbalanced, then the object accelerates. It speeds up, slows down, or changes direction. That's the key. This whole idea is so fundamental, it has a name you've definitely heard before: Newton's first law of motion. It's really just a fancy way of saying that objects are kind of lazy. They'll just keep doing whatever they're already doing, whether that's sitting still or cruising along, unless an unbalanced force, what we call a resultant force, comes along and messes things up. And that resistance, that stubbornness to change what it's doing, that has a name too: inertia. The more massive something is, the more inertia it has, which means it's harder to get it to change its motion. It's exactly why it's way, way harder to push a stalled truck than it is to push a shopping cart. Okay, so that totally covers balanced forces. An object just keeps on keeping on. But what about when things are unbalanced? When they start to speed up and change direction? There has to be a rule for that too, right? Oh, there is. And it just happens to be one of the most famous and powerful equations in all of science. F equals ma. Force equals mass times acceleration. This elegant little formula is the absolute key to figuring out exactly how much an object will accelerate based on its mass and the total force you're hitting it with. Let's make this real. Let's say you've got a 5-kilogram mass and you want to make it accelerate at a rate of 2 meters per second squared. How much force do you need? Well, you just multiply them. 5 times 2 is 10. You need a force of 10 newtons. That's the standard unit we use to measure force. It's that simple, that predictable, and that powerful.
And that brings us to the grand finale, Newton's third law. You've definitely heard some version of this before. For every action, there is an equal and opposite reaction. It just means that forces are never lonely. They always come in pairs. You literally can't push on something without it pushing back on you.
Now, there are a few key rules for these action-reaction pairs. The two forces are always the same type. They're always equal in strength, and they always point in opposite directions. But here is the most important part, the one that sometimes trips people up. They always act on different objects. Your foot pushes on the earth, and the earth pushes back on your foot. Two different objects.
And once you know to look for it, you see this law everywhere. When you walk, you're actually pushing the entire planet backward with your feet, and it's the planet pushing you forward that makes you move. When you swim, you push water back, the water pushes you forward. It's even how rockets get to space. They push hot gas down with a massive force, and that gas pushes the rocket up. It's pretty amazing. So really, when you boil it all down, from the simple act of getting out of bed to the cosmic dance of the planets, forces are the reason. They are the why behind every single change in speed and every single change in direction that we see all around us.
So let's just do a quick recap of what we've covered. We know what forces are and the different types, we get the huge difference between balanced and unbalanced forces, and we've walked through all three of Newton's game-changing laws: the law of inertia, the incredible F=ma equation, and the law of action-reaction.
But I want to leave you with one last thought. Newton's laws are, without a doubt, incredible. They perfectly describe how things move when forces act on them. But they don't really explain what those forces, especially a mysterious one like gravity, actually are. They give us the rules of the game, but they don't tell us where the game itself came from. And that is a whole other story.